Let us study dielectrics and polarization. Dielectrics are non-conducting substances. In contrast to conductors, they have no or negligible number of charge carriers. In conductor, when an external field is applied, the free charge carriers move and charge distribution adjusts itself in such a way that the electric field due to induced charges opposes the external field within the conductor. This happens until in the static situation the two fields cancel each other and the net electrostatic field in the conductor is zero. In dielectrics, the free movement of charges is not possible when dielectrics are introduced to an external electrical field. It turns out that the external field induces dipole moment by stretching or reorienting molecules of the dielectric. The collective effect of all the molecules' dipole moments is net charges on the surface of the dielectric which produce a field that opposes the external field. Let us study about nonpolar molecules. In nonpolar molecules, the centers of net positive and negative charges coincide. CF3 and CCl4 are some examples of nonpolar molecules. The molecule then has no permanent or intrinsic dipole moment. Let us study about polar molecules. In polar molecules, centers of positive and negative charges are separated even when there is no external field. O2 and NH3 are some examples of polar molecules. Such molecules have a permanent dipole moment. Let us study about dielectrics with nonpolar molecules. In an external electric field, the positive and negative charges of a nonpolar molecule are displaced in opposite directions. The displacement stops when the external force on the constituent charges of the molecule is balanced by the restoring force. The nonpolar molecule develops an induced dipole and dielectric is said to be polarized. Let us know more about linear isotropic dielectric. When the induced dipole moment is in the direction of field and is proportional to the field strength, it is called as linear isotropic dielectric, where P is the dipole moment and E is the magnitude of electric field. Let us study about dielectric with polar molecule. In the absence of external field, the different permanent dipoles are oriented randomly due to thermal agitation. So, the total dipole moment is zero. A dielectric with polar molecules also develops a net dipole moment in an external field but for a different reason. Let us know more about electric susceptibility. In either case, whether polar or non-polar, a dielectric develops a net dipole moment in the presence of an external field. The dipole moment per unit volume is called polarization and is denoted by P. For linear isotropic dielectrics, P equals Xc into E, where Xc is a constant characteristic of the dielectric and is known as electric susceptibility of the dielectric medium. It is possible to relate Xc to the molecular properties of the substance, but we shall not pursue that here. How does the polarized dielectric modify the original external field inside it? The field causes a uniform polarization P of the dielectric. Thus, every volume element delta V of the slab has a dipole moment P into delta V in the direction of the field. The volume element delta V is macroscopically small but contains a very large number of molecular dipoles. Anywhere inside the dielectric, the volume element delta V has no net charge, though it has net dipole moment. However, at the surface of the dielectric normal to the electric field, there is evidently a net charge density. Let us know more about dielectrics and polarization. Thus, the polarized dielectric is equivalent to two charged surfaces with induced surface charge densities, say sigma p and minus sigma p. Clearly, the field produced by these surface charges opposes the external field. The total field in the dielectric is thereby reduced from the case when no dielectric is present. You should note the surface charge density plus minus sigma p arises from bound but not free charges in the dielectric. Let us know more about dielectrics and polarization. Thus, the polarized dielectric is equivalent to two charged surfaces with induced surface charge densities, say sigma p and minus sigma p. Clearly, the field produced by these surface charges opposes the external field. The total field in the dielectric is thereby reduced from the case when no dielectric is present. You should note the surface charge density plus minus sigma p arises from bound but not free charges in the dielectric.